organic chemistry too. That probably wouldn't happen, but anyhow. Okay, let's take a look at some practice problems. And these practice problems are posted in the Chapter 16 module of our class. So let's take a look. It says predict the possible products for the following reaction and provide a curved arrow mechanism for the formation of these products. We have a conjugated diene, and we're treating it with HBr. And we're going to add the proton or a proton to one of these double bonds in such a way that we end up forming an allylic carbocation. If I add a proton to this carbon, that means I'm going to make a carbocation here, and that carbocation would be allylic. So let's draw the mechanism of the proton transfer. So we're going to add a proton to this carbon, and we're going to end up with this carbocation. So let's draw it out here. It's going to look like this, and there you have it. Now, you can draw the resonance structure of this, and I'm going to do it, and then I'm going to erase it, and you're going to see why. Since you end up with this allylic carbocation, if you draw the resonance structure of it, you end up with a resonance structure that is identical to the first one, right? If you were to take this molecule or this ion and rotate that 180 degrees, you'd end up with this. And so I'm just going to leave the one resonance structure, the one I have in the blue circle, because whether the bromide attacks here or here, you end up with the same product. Okay, you end up with the racemic mixture either way, because remember the carbocation, its carbon is sp2 hybridized. So I'm just going to erase the second resonance structure. Again, it's not required in this case. And we're going to say the bromide is going to come in as a nucleophile. I'm going to remove that resonance arrow, and we're going to, oops, that was wrong. I need my pen. There we go. So we're going to have our nucleophilic attack. And again, that bromide can attack from either face of that carbocation because the carbocation is trigonal planar. And so we end up with a racemic mixture. So racemic mixture. Now what we're going to do is we're going to show the proton transfer occurring on this double bond. So let's redraw the molecule. Put it right here. And again, we want to add the proton to whichever carbon is going to produce an allylic carbocation. And thus the one I want to add it to is going to be this carbon here, so that I'll end up with a carbocation over here. Let's draw that arrow. So it's going to look something like this. There's my proton transfer. And let's draw the carbocation. I have my positive charge here. I still have this double bond. But now you see that I've got my allylic carbocation. And let's draw the resonance structure of that allylic carbocation. So I'm going to draw a curved arrow. And I'm going to draw the other resonance contributor, which is going to look like this. So I still have my geminal dimethyl, my double bond here, and my positive charge is here. And so you can clearly see that these two allylic carbocations are very different from one another. And both of those can undergo nucleophilic attack by the bromide. So I'm just going to put Br minus here, Br minus here. And I'm going to erase the resonance arrow that I had. Just draw the nucleophilic attack here or here. Again, our bromide can attack from either face of the molecule because a carbocation is always sp2 hybridized. And so I'm going to end up with this compound, with my double bond here, geminal dimethyl, and this is going to be racemic, again, because this bond could be R or S. And then over here, I'm going to end up with the nucleophilic attack at this carbocation that I drew. And again, the bromine could be on a dash or a wedge. It could attach or attack from either face of the molecule. So I get a racemic mixture here as well. And thus the answer is I get this compound as a racemic mixture. I get this compound as a racemic mixture. And I also get this compound as a racemic mixture. So we end up with a total of 6 possible products or 3 racemic mixtures. All right, next one, it says predict the major product for the following reaction. Remember that when we do the addition of HCl across a conjugated diene at 0 degrees Celsius, 0 degrees Celsius, it means that our major product will be the 1,2 adduct, or what we call the kinetic product. Kinetic product. Now keep in mind that this diene is symmetrical, so it doesn't matter if you add the proton on this double bond or that one, you end up with the same thing either way. So we just need to show the addition of HCl across one of those double bonds to produce an allylic carbocation. Let's do that. Let's add it to this carbon, which would produce this allylic carbocation. So we end up with this here. Here's our allylic carbocation. And now our nucleophile, the chloride, is going to come in and it's going to attack where the carbocation is. Why is it going to attack there? Because we're at 0 degrees Celsius and we're going to get 1,2 addition. Here's carbon 1, here's carbon 2. On carbon 1, we already added this hydrogen. And so now on carbon 2, we're going to add the chloride. Let's draw our chloride ion. Put in all my lone pairs, and my nucleophile, my chloride, is going to attack at carbon 2 to give me the 1,2 adduct. Let's draw our final product, which will look like this. And there you go. There's our final product. So again, it's the 1,2 adduct, and we get the kinetic product because we did the reaction at 0 degrees Celsius. Somebody says, what would happen if it wasn't symmetric? If it wasn't symmetric, we would get 2 different 1,2 adducts in that case. And we never covered, which one would be major and which one would be minor, but whichever one would produce the more stable carbocation, or sorry, the more substituted double bond in the resonance structure, that would produce, no, sorry, if it's 2 different 1,2 adducts, whichever one produces the more stable carbocation would produce the major product in that case. All right, let's try the next one. Same question, but now we're going to make the 1,4 adduct because we're at 40 degrees Celsius. 40 degrees Celsius, again, we're going to make the 1,4 adduct, also known as the thermodynamic product. All right, so let's do it. The first step is identical to the last question. We're going to form an allylic carbocation. Let's do that. Same carbocation we saw in the last problem, like this. But now we're going to make the 1,4 adduct. We've already added the hydrogen to carbon 1. Now our nucleophile is going to attack at carbon 4. Well, it certainly can't attack at carbon 4 in this structure, and thus we have to draw the resonance structure. So let's draw the other allylic carbocation, which is going to look like this, where we have the double bond here, like that. And now we have our positive charge on the end of the molecule, like that. And now we have our nucleophile, our chloride ion, which can come in and attack our carbocation. And that gives us our product, the 1,4 adduct. Oops. There we go. And there you have it, the 1,4 adduct. Again, you see that we added the hydrogen at carbon 1, 2, 3, 4, and the chlorine is at carbon 4. Question 4, predict the major product of the following reaction and explain why it's the major product. Well, again, we're going to get the 1,4 adduct because we're at 40 degrees Celsius, so 1,4 adduct, which again is the thermodynamic product. So first, let's draw the addition of HBr across one of these double bonds to give us an allylic carbocation. Since there is a plane of symmetry down this molecule, it wouldn't matter where you added the proton. As long as you either add the proton here or here, you're going to end up with an allylic carbocation. Doesn't matter which side. I'm just going to add it to the top, but again, it doesn't matter at all. I'll draw my HBr molecule. And let's draw the proton transfer like this, and let's draw our allylic carbocation. So we end up with something that looks like this. We have our carbocation here, and there we have it. But remember, if we're at 40 degrees Celsius, what we're going to get is the 1,4 product. Right? And the 1,4 product, the 1,4 adduct is going to be more stable. Why? Because if you look at the double bond here, this double bond is tri-substituted. However, when we draw the resonance structure here to show the carbocation that would result in the 1,4 adduct, we end up with a tetra-substituted alkene. So we have 4 carbons on that alkene, and we have our carbocation here. And so now we have a more stable alkene. So when our nucleophile comes in, which is the bromide, it's going to attack at carbon number 4. Again, if it helps you, you can always go ahead and number the carbons. 1, 2, 3, 4. The 1,4 adduct. I have my carbocation at carbon 4. My bromide is going to attack at that carbocation, and it can attack from either face of the molecule and produce a stereocenter. And thus, I'll end up with a racemic mixture. So racemic mixture, just like that. Again, this is the major product. They're asking us for an explanation because we're at 40 degrees Celsius and we end up with the thermodynamic product, the product that is more stable. The 1,2 adduct, if we just draw the 1,2 adduct, which wouldn't be formed, might be formed in a small amount, but the 1,2 adduct would be this compound, right? And if we compare the two, oops, did I put a chloride when I meant to put a bromide? There we go. If we compare the two, you see that this double bond is tri-substituted and this one is tetra-substituted, and therefore it is more stable. So this is our thermodynamic product. I'll just go ahead and ask my students about this one. Could anybody tell me which one of these would be the least reactive Dienophile in a Diels-Alder reaction? Remember that we want our Dienophile, we want it to have some kind of electron withdrawing group, something that's going to pull electron density away from the double bond. Is there anything here that has a group on it that would not pull electron density away? Well, if we look at the first two, they both have electron withdrawing groups on them because they both have carbonyls. Carbonyl, we know, is an electron withdrawing group. And so we know that this is going to be a reactive Dienophile. The same thing here, we have a double bond or a carbonyl here. And so that's electron withdrawing. And we saw before that when we have a nitrile, right, that you can draw a resonance structure for that. So if we have this nitrile like this, we can do the same thing where we draw something like this. So we see that it is electron withdrawing. So we would end up with something that looks like this, where we have a double bond to a carbon. We have another double bond like this to another carbon. And then we have a double bond to the nitrogen, which looks like this. We have a positive charge here and a negative charge up here. So that definitely is electron withdrawing. And if we go to the one with the nitro group on it, well, a nitro group is an electron withdrawing group, right? Because nitro is where we have a nitrogen with a positive charge on it. If you have something with a positive charge, you can bet your bobby socks that's going to pull electron density away. And we could draw the resonance arrows for that, where we show the negative charge or the electron withdrawing nature of the nitro group. So we end up with this, and we have our double bond here, and we have a positive charge down here. However, if we have a methoxy group, that is not electron withdrawing, that is electron donating. You could draw resonance arrows where we show the donation of electrons. And so methoxy is electron donating. And all of the other substituents on these dienophiles are all electron withdrawing. And so the answer would be number 4, the one with the methoxy. Methoxy is electron donating, not electron withdrawing. And so it would be a very poor dienophile. Next one, I'll ask my students, which one of these dienophiles is the most reactive? Is there any dienophile that you would think would be more reactive than all the others? Remember, we're looking for something, the more reactive a dienophile is going to be, it's going to have a more electron withdrawing group on it. Could anybody tell me which one of these? Yeah, the answer is number 3, isn't it, right? Number 3 is the only one that has 2 electron withdrawing groups on it. You've got a carbonyl going this way, pulling electron density this way, and you've got a carbonyl over here. There are no electron withdrawing groups on 1 or 2. There's an electron donating group on this one, for Pete's sake, and there's no electron withdrawing group on this one. But in the third one, we have 2 electron withdrawing groups, so it is definitely going to be the most reactive dienophile. Next one just asks us to draw the product. And remember that when we have an alkyne as our dienophile, that we're going to end up with a 6-membered ring with 2 double bonds. Namely, we're going to end up with some kind of 1,4-cyclohexadiene product. You can practice drawing your curved arrows as always. We form a sigma bond, break this pi bond, make a sigma bond, take this pi bond and make a new pi bond. Here we go. And remember that this is an sp2 hybridized carbon, therefore we don't have to worry about dashes and wedges. We just put our methyl ester up here like that. And there you go. There's the product of that reaction. The next one is kind of interesting. We have this really cool dienophile here where we have 2 nitriles. I mean, they've kind of drawn the entire Lewis structure here, but you could just draw it like this. I mean, it's the exact same thing, okay, as this, identical. They're just drawing all the pi bonds out explicitly. Anyhow, another chance to practice our curved arrows. And remember that now that we've got a cyclic diene, we're going to end up with a bicyclic product. We form our sigma bond, we make another sigma bond while we break a pi bond, we move this pi bond, and we end up with a bicyclic product, but now we have 2 6-membered rings. We have one 6-membered ring like this, and then we have the other one, which is going to look like this. So 2 6-membered rings. We've got a pi bond here. We only broke one of the pi bonds here, and thus we have a pi bond here. And since both of these carbons are sp2 hybridized, we don't have to worry about endo or exo. It doesn't even come into our discussion. We have our nitrile here and a nitrile here. And there you have it. Okay, let's move on from there. Question number 9. Predict the major product for the Diels-Alder reaction here between cyclopentadiene and this dienophile. So let's see, we've got our electron withdrawing group here, so that looks good. There you have it. Now we do have a chlorine here, Caitlin, so that is electron withdrawing. However, the carbonyl is going to end up in the endo position because it forms the favorable interaction between the double bond and the carbonyl and the pi bond that's being formed. So let's just see here, and let's practice drawing our curved arrows. So same thing, probably like the 20th time we've done this today, maybe more. And since we have a cyclic diene, we're going to end up with a bicyclic product. We're going to have a 5-membered ring like this, and then we're going to fix our 6-membered ring like this, put our pi bond down here. And remember that this group with the carbonyl is going to end up in the endo position. So I'm going to draw it going down in the endo position. Here's my carbonyl and my methyl group, and my chlorine is going to be in the exo position. Now, of course, I can also get the enantiomer of this molecule because I could have had the dienophile written like that, or I could have put it like this. Either way, I'm going to get a product, and they're going to be enantiomers of each other. So let me just erase that And we'll put over here plus the enantiomer. Next one, it says we have excess 1,3-butadiene, and we're reacting it with this compound here. And you can see that we've got kind of two dienophiles in the same molecule. We've got a double bond here and a double bond here. And we've got an electron with, we've got an electron withdrawing carbonyl here and another one here. So we can kind of think, if we have excess, you can kind of think of the dienophile, sorry, the diene being here, and then it could also react on this side. It could do two Diels-Alder reactions, right? You could do it on this side, like this, to make a 6-membered ring, and then it could also happen on this side, the same thing, where we make a second 6-membered ring. So we're going to have kind of 3 6-membered rings in a row. You know, the first ring, we're going to have the central ring, and then we're going to have the third ring coming off of here like this. Here's our carbonyl. And what does the rest of the molecule look like? Well, we formed a pi bond over here and a pi bond over here, like that. There we go. Let's see. The next question says, predict the major product of this Diels-Alder reaction. I think we might have done this one already, so I won't spend a lot of time on it. Meaning, I think we did it already today. So we're going to end up doing our Diels-Alder reaction like this, and we're going to end up with a bicyclic product. Technically, it's got 3 rings in it, doesn't it? Because we end up with our bicyclic product like this. I'm going to need to move it to have enough room to draw that we end up with the endo product, where we have our 5-membered ring pointing down like this. This is endo, and of course we have the hydrogens in the exo position. I'll just scribble them in like that. Next one asks us, which diene and dienophile would be used to make this Diels-Alder product? You can see that we have a dash here and a dash here, so that means we're going to start with a cis alkene, and we could do our retro Diels-Alder arrows like this, this, and this, and then we just draw what we'd end up with. We would end up with our classic 1,3-butadiene, and we would end up with this dienophile, which is a cis dienophile. I don't know how that happened so quickly, but anyhow, like that. And there you have it. All right, so those are the starting materials for that reaction. Question number 13, same thing. Which diene and dienophile would we need to make this product? Here's our 6-membered ring. Just going to practice drawing our retro Diels-Alder arrows. We're going to break this sigma bond. We're going to break this sigma bond, and we're going to move our pi bond over here. And so what would the reactants look like? Our diene would look like this, and our dienophile would just be ethylene in this case. And the last one, we end up with an endo product here because we have that favorable interaction between the carbonyl and the pi bond that would be formed. We can take the reactants and put them together and heat them up. So let's draw our retro Diels-Alder arrows. This, and let's draw the reactants. So we would have 1,3-cyclohexadiene is our diene, and our dienophile would be this compound. And there you have it. That's all the solutions to all of these practice problems. And I will post these to Canvas. All right. Are there any questions? Oops. All right. Any questions about those? Because that covers everything. Right. Sorry, I can't see the chat. Let me open it up. Nope. Okay. Well, if there's no questions, I'm going to call it a day. That finishes up chapter 16. I'll work on the chapter 16 homework tonight, and I'll probably post it either tonight or tomorrow morning. And the chapter 16 quiz will be on Monday. So I recommend getting quiz 13 done sooner than sooner than later. But I understand that people have lives and jobs and families and everything going on. So if you need to do it on Sunday, by all means, do it then. All right. And if you come up with any questions over the weekend, if there's something you're struggling with, don't hesitate to write me an email, and I'll do my best to answer any questions you have. All right. So am I still recording? Sugar. Stop recording.